Okay, the last thing we're doing in this course is the divergence theorem. And if you've gotten over the shock of Stokes' theorem, the divergence theorem shouldn't be too bad. Okay? So one thing I kind of recommend you do, I mean, if you've been doing physics, you know how electric fields diverge from the charge distribution and stuff like that, but not everybody is aware of that. So the simplest thing I can think of is you've got a surface somewhere in space. It's a closed surface, and it's not too complicated of a surface. Doesn't have any holes through it or anything like that, okay? Although that can be dealt with. But just think of, you can think of a sphere if you like, but think of a sphere that's been gouged out a little, or, bulged out a little here and there. So, whatever, a cylinder that's been kind of deformed. And then imagine you turn on a light bulb inside that cylinder. Okay. So the light is producing 100 watts of energy. Okay. Well, assuming there's nothing to scatter the light, just say it's in a vacuum, then eventually that whole shape is going to have exactly 100 watts passing through every point. Now, it's going to take the light longer to get to some points than other points. I didn't say where it is inside, but you take the most distant point, figure out how long it takes light to get to that point, then every time after that, that whole 100 watts is going to be flowing through that surface. Okay. You can also think of the light in a small circular angle. Just think of a small cone, very thin cone, circular. Okay. So just take, two lines that are almost parallel and rotate them about their central axis. And you get what we call solid angle. Okay. Then the share of the light that's flowing into that solid angle is going to eventually flow through the boundaries of the region, okay? Because that little thing is going to intersect the region out there somewhere. Now, when it intersects, maybe it's going to intersect at a right angle. Surface might be at a right angle, okay? Or the surface might be at some other angle, okay? So that's just an image. And that's an example of a divergence. Your light flux is diverging from that point. Okay, now when I say you turn on a light, think of a light bulb and stuff. Well, an actual light bulb is going to shade part of three-dimensional region. So just imagine a point source of light, just a LED there, some kind of spherical LED that produces light and makes it shine in every possible direction. Okay. I just think a little glowing sphere. Nice and symmetric. Okay, well, an electric field acts a lot like that. Okay, you put a charge here, and you have electric field lines diverging from the charge. They diverge. They spread out. Okay, just the length of the light diverges. It spreads out. So the divergence theorem says that the blocks of a field F, I'll put X, Y, Z coordinates on it. Okay. flux through a closed region of space. And there's some restrictions on what we might mean by closed region of space, because regions can get very complicated and confound everything. But if you just think of any region that you're likely to visualize, if you're not trying to visualize really weird regions, and your book gives you more detail on what the restrictions on those regions might be. I don't want to. We've had too many missed classes, closings and things to really be able to spend a couple of days on the Stokes theorem, a couple of days later work it's there. So we'll just get the essence of it as most engineers would use it. Okay. If you're going to be a data scientist, you might want the more complex stuff. And if you're engineering multidimensional surfaces, okay, in one way or another, you'd want a little bit more, but you would probably be taking a much more advanced course. And this should give you the basics. Okay, so anyhow, the flux through the surface of a closed region of space. It's equal to the total divergence of that field within the region. So it's like how much light is shining through the boundaries of this region after sufficient time has been allowed for the light to get to every point of the region, is the sum of the light produced by every source within that region, okay? By every little bulb. Just imagine a bunch of little bulbs, or even a continuous glowing gas or something, transparent but glowing, and work out the details of that. Good luck. But okay, makes sense. Okay. Now, if it's a continuous region, this would be like the continuous function. You could say the total flux through the thing is the sum of all the discrete regions, sum of all the bulbs. Let's say you got 10 million bulbs. You just add up how much power each bulb produces, and there it is. Okay. You don't have to know where they are or anything. The closer a bulb is to this part of the surface, the further it's going to be from this part of the surface, and it all balances out magically. Or look at the semi-rigorous proof your textbook supplies. If you want to go over that, yep, just ask. Okay. So that's the feel of it. The mathematical statement is triple integral over your region, which I think you would. Of F. What's the divergence of F? Well, no, divergence is del dot F, right? And it's a scalar quantity. Okay, unlike the curl, which we use Stokes theorem, that's a vector quantity that you're integrating over a surface, and you're integrating its normal component over the surface. Okay. And the function F is a vector function, so it can be integrated around the boundary of that surface. All right. So we say that this is equal to the double integral over the surface, and it's a closed surface, so I'll make that closed. Circle there means closed surface. There's a single integral means a closed curve. If you put a circle on this, that means you have a closed three-dimensional region in four-dimensional space. And we don't talk about that in this course, except say, yeah, it's there, and we can extend this into differential geometry and all that stuff. Something I don't know a lot about it. Um, okay. So what do we integrate over the surface? We integrate dot NdA or the integral of f dot d capital S or d capital S just includes the whole NdA. Okay. And you see both notations. They mean the same thing. A ds with a vector with an arrow over it means surface area increment along with a direction, a normal vector. Okay. And there, again, there's subtleties of orientation and stuff like that that I'm gonna let you read about, that we're not gonna take too much time distinguishing because they're all fairly obvious within the context of the problems to be assigned. Okay. So that's the divergence theorem. This means if we want to find the flux through the surface, we can integrate the divergence through the region. If the integral of the divergence is complicated, but somehow this is simpler, we can calculate the integral of the divergence by doing the surface integral. Okay, we can do one or the other or both. Now, the first, I think, generally when I get home is when I post the assignments. And I've got to get used to the fact that since I had to change my network password, the VPN that I use isn't working. So I'm a little delayed in doing some of those things. So, and I'm just saying now that I don't remember. I did everything last night and this afternoon I'll get it all up on the websites. But I'm like getting stuff from yesterday, maybe even from the day before. So I don't remember if it's this section or another section, but pretty sure it's this section where I gave you at least half the assignments verify theorem, meaning do both of these intervals. Show that they're equal. That's the convincing thing. Then I tried to have at least one problem where we had to do this in order to get this, and one where we had to do this in order to get this. It might have been the Stokes there. I don't remember. Okay. I'll remember what I posted. That's what I would attempt to do. I would have for either Stokes or Green's theorem or the divergence of Green's theorem. But I would have you verify by doing both integrals, and then give you a case for one integral. Tells you what the other is. Okay. All right. Well, let's just do a simple integral. Let's just say f of x, y, z equal this standard sphere, radius 3, center 2. Okay. First of all, surface is described by this. And this is a description of the circle down in the XY plane. I'm not going through details of this, but if you need me to explain more details, I will. We'll have time for questions next week if you're fuzzy at some of those details. It's a good time to ask them, but if you want to ask them now, okay. That's just whatever. Okay. So there's our description of the surface. And we're going to easily be able to calculate the normal vector and so forth. And I guess we use R, which would be a function of x, y. And we can do our Tx and Ty vectors cross their cross product, or we can just hand wave and see what the normal vector is for any given surface element. This being radial, this field is always normal surface. Okay. And I chose this example because we don't actually have to set up an interval and do it in order to get the flux through the surface. Anyhow, there's what we need along with the function in order to get the surface. Okay. And this example is about as simple as an example could be. Just to get a feel for it. Okay. There's the rain. There's a rumor that was going to happen. Okay. Volume. Negative 3 y square root of 9 minus negative square root of 9 minus x squared, root of 9 minus x squared, and c. And incidentally, this is actually easier in spherical coordinates. Even at this stage of the course, generally find rectangular easier to visualize. So there we have it. Make sense? Well, then, del dot F is just 3. See that clearly? Just partial with respect to x. I dotted with this gives you x, partial with respect to y, j. Okay. If you don't instantly see that that's 3, you can work a little more with the divergence. So I'm just going to assert it. If you don't see it, you need to refresh it. Okay. And if you want to stop me and say, hey, please refresh me now, I just can't get through this without seeing it refreshed, just say so. I'll do it. It's not a problem. But I think it's almost trivial not to be embarrassed if you don't see it. But look at it and see it's trivial. Okay. So there's your del dot F, so that the integral over the region, which is 3 times the integral dv, which is just 3 times volume, which is 4 pi r squared. Our volume is 4/3 pi r cubed, right? 3 takes care of the 4/3. It's 27, so I think it's 185. Now, we will need to set up the interval, but it's obvious how to set up this interval. Okay. And if you haven't done this interval, just, dz, dy, dx, okay? With these limits, to find that it is 4/3 pi times 3 cubed. Then you, okay? I thought it was, I really wanted to know where that 4/3 pi r cubed came from. I could see the proof of the way the Greeks did it, solid geometry. Somehow it didn't really click. They did this integral, say, oh, why hasn't anybody bothered with solid geometry? There it is. Well, that was stupid because there were a lot of reasons. My reaction there was punctured by ignorance. Okay, there are a lot of reasons to understand the solid geometry. Stretch your mind in a different way. Okay, end of digression. We see that unless I've done something completely stupid here, first the divergence is 3, and if we multiply that by the volume, this is what I think we get. Okay. Okay. Then the integral over the surface area. Well, we could do our Tx. That's actually kind of the easiest way to do it. We just take the derivative of this respect to x, we get I plus x over the square root of 9 minus x squared minus y squared. Times k. The way the x does this, the x and so forth. Well, that's it. Okay. And then ty is going to be j plus y over the square root of the same thing times k. So the magnitude of Tx, well, let's do Tx across T1. Okay. I'm just using the distributive law. It's going to be this crossed with this plus this crossed with this. Okay. So take I cross j. That's going to give you k. Then you're going to have y over that square root times I cross k. Then you're going to have this k cross j with this coefficient. K cross j is negative I. And then it's going to be K cross K, which of course gives you 0. It's negative y over that square root. Okay, it's not, I mean, was right, it's negative x I yj over that square root plus k. Give you a second to process that and make sure I didn't do something stupid. You will notice that, to my discredit, I just didn't take count of the negative sign, even though I kept looking at this and said, well, those should have the opposite sign. But that's not what comes out of the, well, that is what comes out of the function. Okay, the R function. Take a derivative with respect to x with a negative x squared in front of there. You get a negative here and a negative here. I had a positive before. And that's going to make these positive, and now things are going to look about right. Okay. So I'm fairly comfortable with how I was really uncomfortable there. I was trying to read through what I thought was a pretty obvious explanation of the text. Make sure I had lost track of something. It's hard to find things in that text. Okay. I wanted to get back to the root, so I kept looking backwards until I didn't see t theta cross tx or whatever. Well, that's beside the point. Okay, so we got this, we got this. So now the integral over the surface of f dot n dA or f dot ds is the integral over the surface of f, which is xi yj plus dk. Going to then be dotted with your ty cross tx, and tx cross ty, dotted with I. The I goes there, the arrow goes above, over that square root that I'll fill in when we need it, and then plus yj over the square root, etc. Plus k. Okay, now the surface here is defined thus. So we're going to integrate this with respect to x and y from -3 to 3 with respect to x, and from negative square root of 9 minus x squared, square root of 9 minus x squared dy. X squared plus y squared. Now I said plus zk. Z is the square root of 1 over square root of x z squared of 9 minus x squared minus y squared to the surface, right? Right in 9 minus x squared minus y squared. Not go through the rest of this because this is a little bit of a tricky integral. It's just analogous to integrating like u squared over the square root of a squared minus u squared. Okay, yeah, hang on. I'm sorry, I'm just not very alert. I chose this surface because the flux should always be parallel to the normal vector. Okay, the function should always be parallel to the normal vector here because everything's radial, which makes this thing kind of trivial. Okay. Now, when I went through all the machinery of setting this up, the one thing I didn't do was put all this over a common denominator. Okay. And what I find is I've got the common denominator I multiplied by common denominator over common denominator. Okay. Which gives us this. And then you can kind of change this to polar coordinates. So you got 9 over 9 minus r squared here. And you can do a trig substitution that r equal cosine theta or whatever and integrate it. Okay. What it actually then comes out as the magnitude of the flux vector is always 3. It's always parallel to the normal because the field is radial. Okay, the field is always perpendicular to the surface of the sphere. Radial vector is always from the center is always perpendicular to the surface of the circle or sphere that it lives on. So even though we get some slight complications here in doing the integral, yeah, you got to do some trig substitution and stuff. And when you have two variables, I think it's a little trickier than I really want to lay on you. But it does come down to what I said. So you could do that. But we know that the surface area is 4 pi r squared. At least you should know that's the surface area of the sphere. Okay. Now, another thing we could have done that would have turned out to be easier would be to parameterize the surface in terms of spherical coordinates. Okay. That's worth looking at. But we don't want to go through those details today. We can look at that next week if that's a source of confusion. What we're really trying to see here is that for this surface, you don't really even need the integrals. It's actually obvious, which is why I chose this and got hung up on it. The magnitude of this on the surface is always 3, and it's always radial. So it's always parallel to the normal vector. So you just take 3 and multiply by the area of the surface. Okay. And the divergence is always 3. So you just take 3 and multiply by the volume of the surface of the sphere. Okay. So magnitude of F is always equal to 3. Its radius is normal. So that the double integral of F dot n dA equals three times the area of the sphere. It's 3 times 4 pi r squared. Which is 108 pi. Is just constant. You end up again with 108 pi into 2 degrees. And if you do this integral and work it out, you're going to end up with the same thing. Got a question? Okay, let's just say that f of x, y, z equals this, where I've got the y in front of I and the x in front of j. What's that do? Well, what's that do to the divergence? Divergence is identically equal to 1. Okay. Parameterizing in terms of X and Y again. Dotting this with your I have the right things. Okay, dotted with your and then it's going to be, well, it's going to be this. And that's going to give you 2xy over that square root. Why? Because you got yi dot xi, which gives you yx, and xj dot yj, which gives you xy, gives you 2xy. And it's over this. And it's plus x squared minus y squared. So this is what you'd be integrating. Okay. With respect to x and y. This integral with respect to x or y is simply a u substitution, let u equal y. Sorry. Let u equal y squared, get it out eventually, so that du is y dy and so forth, and you can integrate, you can get that derivative. And then when you integrate with respect to x, you're still going to have an x over to the next squared here, and you can do that, okay? Then this really kind of easier in polar coordinates, but you can still do it. Could use you could use y equal cosine u and integrate with respect to y. Okay, except it wouldn't be cosine u, it'd be the square root of 9 minus x squared times the cosine of u, which is a little tricky. So my point is, it's easier to use this, which implies that the triple integral of del dot f dv equals 1 times the integral dv equals 36 pi in this direction, 36 pi being the volume of a sphere of radius 3. Now wait, 4/3 pi r squared. Yeah, 36. Okay. I mean, that's a third of the 108, which is how I did it first. When it told me, okay? Okay, got about 6 minutes left. This is a technology problem, okay? I don't know why, because it's much easier. The integral is much easier than anything we've seen so far. All those problems we've looked at so far have a very simple solution, okay? We got this function. Okay, so tell me what's the divergence? What's the partial of this with respect to x? What's the partial of this with respect to y? Yeah, keep using the right finger there. Okay, so divergence is 3. Okay, now the region, let's just use 9 minus x squared minus y squared, which we've used before. This isn't exactly the same. The other one has an upward facing parabola below, I think z equals 4. Okay. And do the volume integral. That's not a paraboloid. That's a stupid series. I'm going to change that just a little bit. Um, Now with this, your volume integral would be the integral from -3 negative square root of 9 minus x squared, square root of 9 minus x squared, and from 0, x squared plus y squared, dz, dy, dx. And there's no real trick to doing that integral. Okay. Another way you can integrate that is by cross section. A paraboloid looks like this, where it actually, the paraboloid is not above the z-axis. It's below z equals 4, so I don't know what I was thinking there. But z goes 0 to 4. Okay. This will be closed. I'm just going to do this by cross section. Okay. Now cross section here at Z. Is a circle of this radius, right? Now, if this is Z, Z equals x squared plus y squared. Then radius is square root of Z. Circular cross section. See, pi Z, so volume equals the integral 0 to 4 of pi Z dz. But go get Z squared over 2 from 0 to 4, which is 8 pi. It ought to be the same thing you get if you do this. Let's make sure that makes sense, because up here it's equals 4. Then you have on the top a circle of radius 4, which would have area 16 pi. And the parabola would fit half of the enclosing cylinder, which makes a certain amount of sense. Seems like it should be a little higher. Anyhow, just illustrating an alternative way to find the volume of the region, because so if this is correct, I say it seems a little low, I'm not sure why. There's my picture of it. It means is the integral of the normal component through this paraboloid, which is kind of complicated. The direction of this function is a little weird. It's got some symmetry to it. It's not that weird. But it just means that you triple the volume of the solid. The paraboloid. You get this, which equal the interval over there. Okay. And the area interval, the F dot N thing, gonna be a little more complicated. Okay.